Welcome to this exciting exploration into the world of SLAM. Most people working on SLAM typically rely on Robot Operating System, ROS, and predefined libraries using simulation instead of real-world scenarios. But we decided to take it a bit further, take a different route. We believed that if we wanted to truly master SLAM, we needed to do it the right way, from scratch. Rather than using pre-built templates and libraries, which can be picked up at any time, we challenged ourselves to build a SLAM system manually. Now, we didn't have the budget to buy a professional LiDAR sensor, which can be quite expensive. So we decided to create our own using a servo motor and a time-of-flight laser distance sensor. Along with that, we built a robotic car, calibrated the entire system, and coded the entire SLAM architecture by hand in pure Python. We did not stop there. We also used OpenCV to display the results. Why go through all this trouble? Because real-world data is messy, it's noisy, error-prone, and unpredictable. By learning how to make a DIY sensor work effectively, we prepared ourselves to handle the complexities of real-world SLAM. We implemented particle filters, noise reduction techniques, temporal filtering, and probabilistic methods to refine our data. We also used AI to calibrate and adjust the incoming data, providing us with a cleaner and more accurate experience. On top of that, we applied advanced techniques like erosion to process and refine the probabilistic maps, leading to highly accurate results. The project required a deep dive into the mathematical algorithms, and the only way to fully grasp these concepts was to recreate the entire system from scratch using Python, coding every line by hand. Although many people use ROS, we did too eventually, but our journey began with Python. By the end of this video, you will see how we ported and transferred our Python-based system into ROS on a Linux platform, displayed the results using RVs, and how the entire system functions with nodes, topics, events, and publishers in the ROS environment. Before we get into the ROS part, let's break down how we developed the system in Python. We divided the program into 4 key parts, each serving a crucial role. Number 1, the driver node. This bridges the gap between the program running on the computer and the robot itself. It handles all the functionalities required to communicate with the robot, which is receiving and calibrating data to ensure accuracy. It also sends commands back to the robot when we want it to move. Number 2, the node which updates the grid. This part is responsible for converting all measurements into Cartesian coordinates, updating the occupancy maps, and plotting probabilistic grids that represent free space. It also pinpoints the robot's pose and gives us the grids we need to visualize the environment. Number 3, the node which helps us in pathfinding. This node ensures that we always have the latest path available. Whenever the robot's position, the occupancy grids, or the goal position changes, this node updates the path accordingly. It also listens for mouse clicks in RVs within ROS, allowing us to update the robot's path to any clicked goal position. Navigation. This final part calculates the robot's next steps, how much it would turn, whether it has reached the goal, and in which direction it should move. It uses models that we'll discuss later to send appropriate commands to the robot with the right timing and precision. Additionally, we have published a Python library called Vagabond, which you can use for pathfinding in your own projects. We'll provide more details on these later in this video. So stay tuned as we dive deeper into the technical aspects of SLAM, explore our DIY solution, and reveal how you can apply these techniques in your own projects.
Before diving into the project, let me walk you through how we built the robot itself. To work effectively with SLAM, it is crucial to understand how the incoming data behaves, and for that we needed a reliable distance sensor. Initially, we opted for an ultrasonic sensor mainly because of our previous project, Sarda, which also used ultrasonic technology. That project involved navigation, but it wasn't as advanced as what we are tackling here. Back then, we were just beginning to explore robotics, focusing on basic navigation and mapping. But we are now ready to take it to the next level. We already had the know-how on using ultrasonic sensor to transmit data from the robot to computer, as well as how to drive the mobile robot using motor driver modules. So we began by gathering all the necessary components: DC motor, wheels, battery holders, ultrasonic sensor, and of course breadboards. Initially, our plan was to incorporate 2 distance sensors, specifically ultrasonic sensors, mounted on a servo to rotate and scan the front and the back of the map. However, we later upgraded to a single time-of-flight laser distance sensor for better accuracy. The mobile robot is powered by an ESP32 microcontroller which communicates with the servo, distance sensors and motor driver. We also included a logic level shifter to manage the voltage between 5V and 3V. The robot is equipped with three 3.7V Li-ion batteries and a power switch to easily turn the system on and off.
This time around, we decided to move away from the laminated fiber materials used in our previous robots. Instead, we chose fiberglass for its transparency and increased thickness. The new design included a large chassis to house all the components, with wheels attached and a longitudinal piece that would hold the ultrasonic sensors on either side. We began by working on the ultrasonic sensors, which were mounted on a very thin perforated breadboard. We carefully soldered the two ultrasonic sensors into the breadboard, ensuring they were securely fixed. This setup was then attached to the longitudinal piece of fiberglass. Additionally, we mounted a servo on this longitudinal piece, allowing it to rotate and scan the surroundings. The servo could pivot between 0 and 100 degrees at both the front and the back, providing comprehensive scanning capabilities for the robot.
Initially, the ultrasonic sensor proved to be a poor choice for our project. They were highly unpredictable, noisy and inaccurate, though they did manage to get the job done for a time. However, we soon realized that a time-of-flight laser distance sensor would be a better option. At that moment, we didn't have the upgrade yet, so we worked with what we had, focusing on optimizing and reducing noise to make the ultrasonic sensors function as well as possible. Once the mechanical assembly was complete, we physically tested the servo's rotation from left to right, ensuring it could scan effectively. The data from the ultrasonic sensors was sent to the ESP microcontroller, which then transmitted it to the computer via UDP in JSON format for processing. We faced significant challenges in converting this data into Cartesian coordinates, plotting the points accurately and accounting for various error states. Testing was particularly difficult due to the cluttered environment at home, filled with furniture and small objects that interfered with accurate sensor readings. To address this, we needed a compact, controlled environment where we could effectively evaluate sensors' performance, especially given its limited range. This led us to build a small DIY testing setup to validate our ultrasonic sensors measurement.
To effectively test the ultrasonic sensors, we needed a controlled environment where our robot could move around freely. We repurposed an old TV box to create a makeshift playground. After laying the box flat on the ground, we cut one side to form a small arena with walls for the robots to navigate and scan. The original walls were too short, so we extended their heights by mounting them in pillars, ensuring the ultrasonic sensors could adequately detect and measure distances. To make this setup more functional, we used tape and markers to create measurement guides and ensured the walls were straight as possible. We also covered the corners with pieces of cardboard to smooth out the edges, preventing sound waves from getting trapped or deflected. The result was a well-constructed mini arena where our robot could test its navigation and measurement capabilities. We even added small blocks to simulate obstacles and walls, giving us a comprehensive environment to evaluate how well the sensor performed in detecting and mapping its surroundings.
We ran into a significant issue with the ultrasonic sensors. When we placed them in the arena, their performance was inconsistent. The sensors struggled, especially when scanning corners where the sound waves seemed to get trapped or reflected unpredictably. Additionally, when we tested them against various surfaces like a marble wall, the sensor often failed to detect the surface accurately, leading to unreliable data. Recognizing the limitations of the ultrasonic sensors, we decided to switch to a time-of-flight laser distance distance sensor from a previous project. This sensor promised more accurate and stable measurement compared to the noisy and erratic ultrasonic sensors. We carefully disassembled our old robot, removed the time-of-flight sensor and mounted it on a servo in place of the ultrasonic sensor. This upgrade significantly improved the robot's performance. With the time-of-flight laser distance sensor now in place, the robot's scanning and measurement capabilities were greatly enhanced. But before we dive into the impressive results of this upgrade, let's take a closer look at how we built the robot chassis itself.
Building on our previous experiences with Sarda, our latest robot chassis was crafted with thick, transparent fiberglass. This time we added some modularity to our design or added flexibility. We secured DC motors on either side of the robot and installed a freely rotating wheel at the front and back to ensure smooth movement. This setup also included battery holders, a motor driver and other essential components. To make the system modular, we designed it so that the key components could be easily swapped or upgraded. For instance, we soldered the header pins on a laminated perforated board, allowing us to plug and unplug the ESP32 controller as needed. This plug-and-play approach meant that if we needed to replace the ESP32 or repurpose it for another project, we could simply disconnect it and connect it later. Similarly, for the motor driver, we avoided permanent soldering by using header pins and plug-in connectors. This way, we could easily detach the motor driver if necessary. All the wiring was meticulously routed, secured with zip ties, and organized for a clean, efficient setup. Finally, we mounted the servo and the compact time-of-flight laser distance sensor on the top of the chassis, completing the assembly with a system that was both practical and innovative.
Coding the entire system was quite a challenge, especially with the ESP32's limited number of pins. When using Wi-Fi to broadcast data, many of the available pins were occupied, leaving us with only half of the pins to manage all the functionalities. We had to carefully allocate these pins and write efficient high-speed code to ensure that the scanning and data transmission process were smooth and lag-free. We will dive into the coding details later, but first let's address another major issue we faced. The robot's turning mechanism initially posed a significant problem. The wheel mounted at the back of the robot would rotate erratically and often get stuck, making it difficult to drive the robot straight or turn accurately. Despite both forward motors working in unison, the robot would veer off course. To resolve this, we replaced the problematic wheel with 2 additional motors at the back, giving the robot a total of 4 powered wheels. This adjustment, powered by a single motor driver, provided much better stability and control. With this upgrade, the robot could now turn 360 degrees smoothly and maintain a more stable movement compared to its previous 2-wheel setup with a non-powered third wheel. With the mechanical issue sorted, we were ready to dive into implementing the SLAM system.
Our first major change was moving away from traditional binary occupancy grid and adopting a probabilistic approach. This shift significantly reduced noise and provided a more accurate representation of the environment. We implemented probabilistic occupancy grid and free space grids to better handle the inherent noise in our system. To further enhance accuracy, we employed various noise reduction techniques, including temporal filters, probabilistic filtering. We fine-tuned raw Cartesian coordinate points calculated from the probabilistic grids, addressing minor errors with erosion techniques to eliminate minor inaccuracies. We also developed programs to mitigate clumping artifacts, ensuring that our grid representation aligned more closely with real-world scenarios. There were minor imperfections in our setup, such as the servo not rotating precisely and occasional calibration issues with the LiDAR. To address this, we used deep learning. We designed a specialized model with layers that processed each value independently, reflecting real-world scenario where data points are largely independent. Training this model required considerable effort. We manually measured all the distance by positioning the robot in front of a straight wall and taking multiple observations. The data was then used to synthesize the diverse dataset, which was fed into the model for training. Once trained, the lightweight model was saved and could easily load it for real-time use without significantly impacting performance during operations.
Let's give the details of the SLAM implementation brief. We used historical data and various filtering techniques to achieve a clean and noise-free map for our algorithms. Initially, we employed different types of particle filters to pinpoint the robot's location within the map. Particle filtering was so precise that it could update the robot's position even without odometry information when the robot was moved manually. However, for complex motion and action, odometry was essential. To integrate odometry, we created a model based on simple equation to estimate the robot's movement. Although our robot lacked wheel encoders and gyroscope, we could estimate distance and rotation by controlling motor speed and duration. We use these estimates to command the robot to move specific distance or angles, adjusting commands based on the model's calculations. This model allowed us to update the robot's position in real time on the occupancy grid. In summary, our robot was controlled not by velocity commands but by specific distance or angle commands. We calculated the required parameters for accurate movement based on various measurement and adjustments, which were then applied through the trained model. The particle filters accounted for any small discrepancies, ensuring precise positioning and orientation.
Next, we focused on pathfinding to make our SLAM project effective. We needed a robust pathfinding algorithm to navigate the robots to its goal position. Implementing this was a challenge. We chose A-star algorithm for pathfinding and leveraged our own library, Vagabond, which we developed years ago. Vagabond allowed us to perform pathfinding using A-star algorithm effectively. We integrated functions to find neighbors, calculate costs, and apply heuristic. We ensured that cost calculations minimized unnecessary deviations, directing the robot towards the goal smoothly. We also included a path simplification algorithm that streamlines the path, making it easier for the robots to navigate. This simplified path was then used by navigation module to determine the robot's movements. The navigation system calculated the robot's current position and orientation, determining the necessary turns and adjustments to approach the goal accurately. This process involved iterative adjustments with appropriate weights and feedback control to ensure the robot reached the target position. Additionally, the pre-trained models were used to generate precise commands for the robot. With these systems in place, the robots could autonomously navigate and follow the path effectively, performing multiple maneuvers to reach the goal position with a few specific tolerance.
One of the standout features of this project is the Vagabond library, which simplifies pathfinding tasks. We are excited to release Vagabond to the public, allowing you to easily integrate pathfinding capabilities into your own projects. You can install Vagabond via pip or check out the GitHub link in the video description. Vagabond offers an intuitive way to handle pathfinding problems. The library requires you to define a function that identifies the neighbor of a given node in your graph. You can assign different costs to these neighbors, which helps the algorithm determine the most effective path. With a specific node object designed for pathfinding, Vagabond automates the process of finding the optimal route. To get started, install the library using pip install PyVagabond. Here is a quick overview of how to use Vagabond for pathfinding. You begin by defining your environment, such as a grid representing free and occupied spaces. Next, specify the starting and ending nodes for your path. You then create a function to determine the neighbors of a node based on its position in the grid. For each neighbor, you can set costs that reflect the difficulty of moving to that neighbor. These costs help guide the algorithm in selecting the most efficient path. The library provides methods to execute the A-star pathfinding algorithm, which involves calculating the short shortest path from the start to the end node while considering the defined cost. Once the path is computed, you can visualize it using plotting tools showing the optimal route on a grid. To illustrate, Vagabond can handle tasks like navigating a robot through a grid by calculating distance and adjusting movements to reach the goal efficiently. This example demonstrates how the library can be applied to a grid with different cost values, calculating and visualizing the shortest path between 2 points. Give Vagabond a try in your projects. Just define the necessary functions, install the library, and let it handle the complex pathfinding tasks for you.
At the final stage of the project, we integrated everything into a ROS2 driven program. This required setting up the necessary nodes, topic, publishers, and listeners to ensure smooth operation within the ROS2 environment. To streamline the process, we transitioned from using OpenCV for plotting to utilizing RVs for visualization. To achieve this, we made sure all data being broadcasted adhere to the specific ROS2 data types, ensuring compatibility and proper communication across the system. We developed 4 distinct nodes to handle various aspects of the system. Number 1, the communication node manages the interface between the robot and the driver, ensuring accurate updates and calculations. Secondly, the grid management node handles the probabilistic grids, particle filters, and conversion of distance measurement and information into Cartesian coordinates to track the robot's position. Number 3, the pathfinding node ensures that a viable path is continuously available and updated whenever changes occur in the environment. Number 4, and lastly, the navigation node directs the robot's movement, including how far and in what direction to move, while providing feedback control to adjust the robot's orientation. After conversion to ROS2, we meticulously refined the system to ensure everything functions seamlessly. The final result is showcased in RVs, where you can see the map being plotted and updated in real time.
So that's a wrap. We have successfully built a SLAM system from scratch, demonstrating not only our ability to handle complex algorithms but also our flexibility in integrating with ROS2. From creating and fine-tuning probabilistic occupancy grids and particle filtering to implementing efficient pathfinding and navigations, every step has been a story of innovations and learning. We have showcased how our system can function seamlessly within the ROS2 environment, leveraging RVs for real-time visualization and ensuring precise robot control and positioning. This project highlights our commitment to pushing the boundaries of robotics and automation, and we are excited about the potential applications and improvements that lie ahead.